Good evening to all of you. So today is our week 12, and today we are going to discuss a linear transformations. So here we are going to discuss how we can transform a linear transformation in R1 to R2 to R2, R3 to R3. How we can transform. So there are some theorems are there. So how we can perform a linear transformation. So these things we will discuss today. So first of all, tell me whether my voice is clear or not. Just raise your hand if my voice is clear. So, okay, it's all right. So it's all right. Okay, I'm going to upload the PowerPoint slides. Just wait a minute. So this is a linear transformations. Today we are going to discuss this. And first of all, we will discuss the introduction to a linear transformation. After that, we will discuss the kernel and range of a linear transformation. What are the kernels and what are the range? How we can represent this? We will discuss this. After that, we are going to discuss how we can represent in a matrix to a linear transformations. And after that, at the last, we will discuss the transition matrices and similarity. So let us see the definition or the introduction of a linear transformation. So here it is a little bit definition. It says that a function T that's map a vector space V into a vector space W. And the linear transformation is denoted by transformation of V mapping to W, and V and W are the vector space. So this is a basic concept, so that from this you can understand this is the figure that we are going to say that. So if a mapping from V to W, if we have one set V and we have another set W, and there is a transformation from V to W, that is called, and it is written as transformation from V to W. So then it is called a linear transformation. So in this way we will start. So we would say that it is a linear transformation. Please wait a minute. So I told you that this is a transformation from V to W. So it is called a domain, and it is called a codomain. So from domain to codomain, it is called a transformation from V to W. And the sets from here, a small sets from V. So the images are from V to W. These are the small w. These are the images in the capital W. So this small circle is called the range. And this from this domain, we are moving from this domain to the codomain, and the small circle is called the range. So this is the concept of the linear transformation. So there are two things in a linear transformation. One thing is a domain, and another thing is a codomain. And we have a transformation from domain to codomain, that is called a linear transformation. Now let's see, we will discuss uh, there are some more definitions. Image of V under T. If V is in V, capital V, and W is in capital W, such that transformation of V will be is equal to W. Of course, we will see this. If we have V in V and W in W, then transformation of V will be in W. Yes, of course, we will see. We can see this this definition from our this picture. And similarly, then W is called the image of V under T. Similarly, the next definition is the range of T, the set of all images of a vectors in V, that is called the range. As I showed you in previous picture, this all things is called the image, the range, and the let's see what's in the previous slides. What we said, the set of all images of vectors in V, that is called the range. So range, as I showed you in the previous lecture, this is called the range. And similarly, the pre-image of W, the set of all V in V, such that transformation of V will be is equal to W. So that is called the pre-image of W. Means in the previous slides, the all things, this is called the pre-image. Yani all things pre-image of W, whatever, this is called the pre-image of W. So now let us see a small question. From this small question you can understand. A small question is says that a transformation from R square to R square, such that V will be is equal to V1, V2 belongs to R square, and the transformation will be is equal to transformation of V1, V2 will be is equal to V1 minus V2 comma V1 plus V2. So this is the transformation is given. Let us recall equation number 1. Now there are the questions. There are the two questions are given. The first question is find the image of V minus 1 2. What is the image of V? It will be equal to minus 1 2. And find the pre-image of W minus 1 1 minus 1 double 1 2. So there are the two sets are given, and we have to find the image of and the pre-image. So first one, we will find the image of this is this is capital V, and this is capital W, and this is a small v, this is a small v, and this is a small w, this is a small w. So he wants to find the image of V. So when we find the image of V, that is minus 1 2 here, what is the image of here? So when we find the image, that is the transformation from V to W. So let us see what we do. So v will be is equal to minus 1 2 is given. So let us we take a transformation, apply the transformation of v will be equal to transformation of minus 1 to apply the transformation on the left and right side of. So the transformation can be applied from the equation number 1. We can write that, let us assume that it is v1 and it is v2. So from equation number 1 we can write that v1 minus v2. From equation number 1 we can write like this. Then apply, then put the comma, and then v1 plus 2v2 we can write from equation number 1. It is written everything, v1 minus v2 and v1 plus 2v2. So that is why I write this thing. So now we will add that minus 1 minus 2 will be is equal to minus 3, and minus 1 into 2 into 2 will be is equal to 4, minus 1 will be is equal to 3. So this is the image. Find the image of v. So image of v will be is equal to minus 3 3. So minus 3 3 will be here, like minus 3 and 3 will be here. So now the second question is find the pre-image of w minus 1 1. So what is the pre-image of w? So minus 1 1 here, minus 1 and double 1 here, and he says that what is the pre-image? So means we have to find the pre-image of this. So we will find the pre-image of this. So let us say that, so it is given that transformation of v will be equal to w is equal to minus 1 double 1. So it is given that transformation of v1 v2, it is given from equation number 1, it will be equal to v1 minus v2 comma v1 plus 2v2. It is from equation number 1. We can say that it is given inside the question, and it will be is equal to minus 1 double 1 because of it is the image. So it is given inside the question. So now what we will do, we will compare the equivalent terms. So here v1 v2 minus v2 will be is equal to minus 1, and v1 plus 2v2 will be is equal to 11. So we will compare, the separate terms. So this is the equation number 1, v1 minus v2 will be is equal to minus 1, and v1 plus 2v2 is equal to 11. So there are two equations, two unknowns. So we know how we can solve. So there are two equations we can solve. We will subtract them, minus minus minus, and we will subtract them. We will find v1 2v2 minus v2 will be equal to minus 3. 3v2 is equal to 12, and v2 is equal to 4, and v1 is equal to 3. In this way we will solve that. So this will be the 3 4, the pre-image. This is 3 4 will be the pre-image of minus 1 11. In this way we will solve such type of problem. So hopefully you understand what is the image and what is the pre-image. So in this way we can solve the image and pre-image of the transformation. So any question up to here? Okay, so let's proceed. So up to here, there is a question. I told you that just a transformation is given, equation number 1 is given, and you have to solve some problems with the help of this transformation is given. Now I will tell you what is the linear transformation. When we say that it is a linear transformation, so there is a definition is given. So a linear transformation, we call in short form, I will write it LT. LT means linear transformation. So let's VW is a vector space, and a transformation from V to W is a linear transformation. So there are two things. Transformation of U V will be is equal to transformation of U plus transformation of V. So it says that there are the two properties are hold. First property is that the transformation of U plus V, this is a U plus V, and this will be is equal to U, and this will be is equal to V. So when we apply the transformation from here to here, that will be is equal to transformation of, so transformation of UV is equal to transformation of U plus transformation of V. And similarly, transformation of CU will be is equal to C transformation of U, and the transformation of CU will be is equal to C transformation of u. So this is called the transformation. So it is this one is in the part of v, and this one is the part of w. So these are the two properties. The meaning is that these are the two properties. If these two properties are hold, then we say that it is a linear transformation. Whenever you have to ask the question, prove that it is a linear transformation or not, or you have to ask the question, verify that it is a linear transformation or not. So you have to do these 2 points. You have to satisfy these 2 points. If these 2 points are satisfied, then you say that it is a linear transformation. If any one point is not satisfied, then you say that it is not a linear transformation. Let us see a question. So here it is explaining that a linear transformation is said to be operating preserving transformation of u plus v. For your understanding, it is defining the transformation of u, any addition in v that I show you in previous. There are two things. This is v and this is w. So he says that transformation of u plus v is in v, and after that transformation of u, transformation of v, it is in w. So, and similarly transformation of cu is scalar multiplication in v, and after that, after the transformation, it will be in w. So verify a linear transform. So this is the question number 2. It says that verify a linear transformation from r square to r square. Yani we have to prove that this is a linear transformation or not. So let us assume that it is equation number 1, and we have to prove that whether it is a linear transformation or not. So we know that we have to prove 2 things. Number 1, as I showed you in previous slides, we have to prove these 2 things. If these 2 points are satisfied, then we say that it is a linear transformation. If any one of these points is not satisfied, then we say that it is not a linear transformation. So let us see. So let us see, we will do. So to prove that, first of all, let's assume u is equal to u1, u2 is equal to v1, v2 is a vector space in r square, and v is a vector addition. So you will say that, and you can write u plus v is equal to u1 plus v1, u2 plus v2. Now apply the transformation on both the side, left side and the right side. So when you apply the transformation on the left side, you can write transformation of u plus v. Apply the transformation on the right side, you can write like this. So now when you apply the transformation on the right side, so let us assume that you will assume it will be is equal to v1, and you will assume this it will be is equal to v2. This part you will assume v1, and this part you will assume v2. Now from equation number 1 we can write transformation of v1 v2 is equal to v1 minus v2. So we can write v1 minus v2, then put the comma here, this is the comma, and after that v1 plus 2v2 from equation number 1. We can write from equation number 1, I write it v1 minus v2 comma v1 plus 2v2. In this way we will open this. So now we will separate the u term and v term. Now we will separate the u term on the u1 minus u2, u1 plus 2u2, and separate the v terms separately. Now we will see this. Just see this. What is in which equal? Just see this. What we can write in place of this v1 minus v2, comma v1 plus 2v2. So just compare this with the equation number 1. If we compare this with the equation number 1, so we can write it is nothing, it is transformation of v. And similarly, just compare this with the equation number 1. So we conclude that it is nothing, there is transformation of u. So we will prove that we are proving that transformation of u v will be is equal to transformation of u plus transformation of v. So it is proved, the first point of the theorem. So now let us move to the second point of the theorem. That's if we have any scalar multiplication, if we have any constant c, and we can write cu1 cu2. So apply the transformation on left and right side. So when you apply the transformation on left side, you can write transformation of cu, and when you apply the transformation on right side, you can write transformation of cu1 u2. So when you apply the transformation, so let us assume it will be is equal to v1, and it will be assumed that it will be is equal to v2. So we can write cu1 c. So from equation number 1 we can write cu v1 minus v2 comma v1 plus 2v2. From equation number 1 we can write, from equation number 1 we can write. So that is nothing. We take the c constant outside, that will be equal to u1 minus u2, u1 plus 2u2. So it is nothing, it is the transformation of u from equation number 1. So these 2 points are satisfied. It means that T is a linear transformation. Because of these 2 points are satisfied, that is why we say that it is a linear transformation. So in this way we will prove that. So two uses of the term fx is equal to x plus 1 is called a linear function because its graph is a line. Similarly, fx is equal to x plus 1 is not a linear transformation from a vector space R into R because it's preserved neither vector addition nor scalar multiplication. So next one is zero transformation. Zero transformation means whenever we have a transformation from V to W, such that transformation of V will be equal to 0, it is called a zero transformation. Similarly, next one is the identity transformation. Means whenever we have a transformation from V to V, such that transformation of V will be equal to V, it is called a identity transformation. Now there is a theorem. There are some properties. Property number 1, it says that transformation of V will be is equal to 0. Transformation of 0 will be is equal to 0. Similarly, if we multiply any vector minus V, then minus will be outside and it will be equal to transformation of V. Next one is, these are properties. And if you separate transformation of U minus V will be equal to transformation of U minus transformation of V, and similarly if V is equal to C1 V1 C2 V2 and Cn Vn, then transformation of V will be equal to transformation of V, like this. In this way we can say that. A linear transformation and basis. So the second question is, it says that let's a transformation from R cube to R cube be a linear transformation, such that these are the standard bases. As I told you, 1 0 0 0 1 0 0 0 1 these are the standard bases. So here given that these transformations are given that 2 minus 1 4 and 1 5 minus 2 and 0 3 1. Find the transformation of 2 3 minus 2. So we have to find the transformation of this 2 3 minus 2. So how we can find it? So before going to solve this, we have an idea that we can write 2 3 minus 2 in this way: 2 into 1 0 0, 3 into 0 1 0, and 2 into 0 0 1. So the question is, can we write in this form or not? So the solution is yes, we can write, because of when we multiply 2 into 1, that will be is equal to 2, and when we multiply 3 into 1, that will be is equal to 3, and when we multiply minus 2 into 1, that will be is equal to minus 2. So it means the left hand side and the right hand side are equal. There is nothing changed. So it means you can write in this way. Then there is no any change. So when we write in this way, now apply the transformation on both the side, left side and right side. When you apply the transformation of the on the left side, it will be transformation of 2 3 minus 2, and on the right side it will be equal to 2 into transformation of 1 0 0, 3 into transformation of 0 0 1, and minus 2 into transformation of 0 0 1. That will be equal to 2 into what is the value of transformation of 1 0 0. It is given inside the question. It will be equal to 2 minus 1 4. And what is the value of transformation of 0 0 1 0? It is given inside the question. It will be equal to 1 5 minus 2. What is the value of the transformation 0 0 1? It will be equal to 0 3 1. So in this way we can find the transformation. Now adding all these things. So when you are going to adding all these things, that will be equal to 2 to the 4 and 3 1 the 3, and that will be equal to, here there is nothing transformation, 0 0 1 will be equal to 0 3, it is nothing. So 2 0 0. So what it will be equal to 2 to the 4, 3 4 plus 3 will be equal to 7. We can write like this. Similarly, what is the next one? 2 1 the 2 minus 2, and 3 5 5 3 the 15, and 15, and next 2 3 the 6 minus 2 3 the 6, and what will be total will be when you add, we will get 7, and the last one will be 2 4 the 8, and 3 2 the 6 minus 6, and lastly 2 1 the 2 minus 2. That if you add all them, you will get 0. So 7 7 0, we got it. So it means transformation of 2 3 minus 2 will be is equal to 7 7 0. So in this way we will solve this. Now let's see the another problem. And in the second problem, it says that the function transformation from r square to r cube, yani here it is r square and it is r cube, so is defined by transformation of v will be equal to a v will be equal to 3 0, and it will be equal to, we find tv, so where v is equal to 2 minus 1. And show that t is a linear transformation from r square to r cube. So there are two questions are there. First question, it says that find the tv where v is equal to this. So apply it is given that v is equal to this, so apply the transformation on both the sides. Left side tv is equal to av, it is given. So the value of a is given here, and the value of v is given 2 minus 1. It is given inside the question where v is equal to 2 minus 1. So now multiply this row to this column. So 3 to the 6, 0 1 1 the 0. So that will be equal to 6. After that, 2 multiplied by 1, 2 multiplied by 2, 2 to the 4, and 1 multiplied by 1, that is minus 1, that will be equal to 3. And similarly, next one will be minus 1 multiplied by 2, and then minus 2 multiplied by minus 1, that will be is equal to 0. So in this way we will prove that, we will show that. And lastly, we can say that transformation of 2 minus 1 will be equal to 6 3 0. And the second question is, show that t is a linear transformation from r square to r square. So we know that to show that whether it is a linear transformation or not, we have to show the two things. First thing is, that is, we have to show that transformation of u plus v will be equal to transformation of u plus transformation of v. So we will prove this first point, and the second point, transformation of cu will be equal to c transformation of u. So these are the 2 points that we proved. So that is called, it means it is a linear transformation. So hopefully you understand the concept. What is r square and r cube? R square means we are moving from r square to r cube. Meaning is that here you will see this is in uh, yani r2 to r, yani this is in 2 dimension, r2 2 minus 1. And what is the result? The result will be in 3 dimension, yani 630. So the r2 means you are talking about the yani two spaces, and the R3 means we are talking about the 3 spaces. So that's why it is given a transformation from R2 to R cube. So here we say that this is in two vectors, v1 v2, and our result will be in 3 dimension, it's 630 in 3 spaces. So that is why we say that. So now let's proceed. A linear transformation given by a matrix. How we can represent a matrix? Let A be a m cross n matrix. The function t is defined by transformation of v will be is equal to AV. Is a linear transformation from Rn to Rm. So this is AVA matrix is given, and these are the vectors. So Rm vectors. So in this way we can write that. A linear transformation from m cross n into n cross m will be equal to transformation of A can be written as A transpose a to the power t, or that is a transformation from m cross n to n cross. Show that t is a linear transformation. So whenever we have to show it is a linear transformation, we have to show 2 parts, first part and the second part. From the help of first and second part, we will prove that it is a linear transformation. Now next thing is, what is the kernel and range of a linear transformation? So this is the theorem. This is the definition is given that, as I told you in my face-to-face class, if we have a 2 sets v and w, this is v and this is w, and there are the subspaces of small v, and there are the subspaces of small w. So are the all the images that's images are 0 is called the kernel of T. So where all the images where we got 0, that is called the kernel. So these all things, all the parts are called the kernel, and these are called the range. And so this is the definition. All the images are 0. Transformation, after the transformation we got 0, that is called the kernel. Finding the kernel of a linear transformation, it is given that. So we can prove that with like this, transformation of v will be is ax will be equal to this, and we can prove that kernel of t will be equal to 0 0. So transformation of x1 x2 x3 will be equal to 0 0. We can prove like this. The kernel of a linear transformation is a subspace of the domain. So these things I show you in my face-to-face class. So there are 2 points that we have to remember. Kernel of T is a subspace of V, and the range of T is a subspace of W. So from this figure we got an idea about this, where what is the kernel and what is the range of T. So next theorem is, let its transformation from Rn to Rm be a linear transformation. By given that transformation of x is equal to ax, then the range of T is equal to the column space of A. Range of T is equal to column space of A. So let T be a transformation, be a linear transformation is given by transformation of ax is equal to ax, then the range of T is equal to the column space of A. So find the basis for the range of a linear transformation. So if you remember, we learned the basis in week 5, in week 5 or week 6, how we can find the basis. So I will give you the little bit idea. When we find the basis, we convert the matrix into the row echelon form. After row echelon form, wherever the pivot element, first element, that is called the basis. So here let us see how we can find the basis. So here we will find the basis. We will convert the matrix into the row echelon form. After we are going, this is the main matrix, we are convert the matrix into the row echelon form. This is the matrix, and the first element will be 1 and rest of the element are 0, and the second element will be 1 and the rest of the element are 0. This is the row echelon form. So now what is the basis? So I told you, if you remember, the basis will be the first element, and after that in the second row the first non-zero element, the first non-zero pivotal 1, and in the third row what is the first non-zero pivotal 1, so first non-zero pivotal 1 is, and in the fourth row what is the first non-zero, all are 0, there is nothing. So we have how many ones are there, how many unit ones are there. So at W1 we have 1, at W2 we have 1, at W4 we have a first non-zero 1. So we say that W1, W2 are the basis for the column space V, and in comparison to W1 we can say that C1, C2 and C4 are the basis for the column space A. So in this way we will say that, so 1, 2, minus 1, 0, and these are the basis for the range space. So how many bases? So whatever, C1, C2, C4. So C1 will be 1, 2, minus 1, 0. C2 will be 2, 1, 0, 0, and C4 will be 1, 1, 0, 2, are called the basis for the range. So hopefully you understand this concept. We discussed these things in week 6, if you remember this. Any question up to here? Okay, so let's proceed. Now there are some more definitions are there. What is the rank? Rank means the dimension of the range of T. And what is nullity? Nullity means the dimension of the kernel of T. So transformation of Rn to Am be a linear transformation by given by transformation of Ax is equal to transformation of Ax. Now there is a theorem that is called the rank nullity theorem, and the theorem says that the rank of T plus nullity of T will be is equal to N. If we have a transformation from V to W be a linear transformation of n dimensional vector space into a vector space W, then it is called a rank nullity theorem. This is the rank nullity theorem. Or we can say that dimension of range of T plus dimension of kernel of T is equal to dimension of domain of T. This is called the range. So now the small question from the rank nullity theorem, it says that find the rank and nullity of a linear transformation. Find the rank and nullity of a linear transformation R cube to R cube defined by this. So first of all, tell me what is the rank of this matrix. Rank of this matrix will be is equal to, means if you remember the definition of the rank, the definition is number of non-zero rows. So how many non-zero rows are there? Yes, number of non-zero rows are 2, because of this is non-zero row, this is non-zero row, and this is 0 row. So number of non-zero rows are 2. So rank will be is equal to 2. And what is n? N means how many number of columns are there? 1, 2, 3. So n will be is equal to 3. So we know the theorem. The theorem is uh, rank of A plus nullity of A will be is equal to uh, rank plus nullity will be is equal to n. So when we put the value of rank will be 3, the value of rank will be 2 plus n nullity, and will be is equal to n. N will be is equal to 3. So n will be is equal to 3 minus 2 will be is equal to 1. In this way we can solve this. So that's why we'll say that 3 minus 2 will be is equal to 1. In this way you can solve it. Find the rank and nullity of linear transformation from R to the power 5 to R for a linear transformation. So the same questions from the rank nullity theorem. It says that find the dimension of the kernel of T if the dimension of the range is 2. So the dimension of the range is to find. Then from the rank nullity theorem we find that 5 minus 2 will be equal to 3. Similarly, the second question, find the rank of T and nullity of T is 4. So from the rank nullity theorem, again we will find from the rank nullity theorem we can find it will be equal to 1. And the last question is find the rank if kernel of T will be equal to 0. So again we will apply the rank nullity theorem. We will find that it will be equal to 5. There are some more on two functions are there. So if kernel of T will be equal to 0, then we say that it is A11. Similarly, it is a proof. There is no need to prove going to depth. Similarly, 1 and on to linear transformation. On to linear transformation. A transformation V to V is a linear transformation where W is a finite dimension. And then T is on to if and only if the rank of T is equal to the dimension of W. So there are the theorems are there. So here it says that let linear transformation Rn to Rm is given by transformation of x is equal to find the nullity and rank and of a linear transformation determined whether T is 1, 1, 2 on 2. So there is a question A. So tell me a transformation from R cube to R cube is if transformation from R cube to R cube, because of in rows we have 3 columns, in columns we have 3, or in rows we have 3 columns, 3 rows, in columns we have 3 columns are there. So that's why we say that a transformation from R cube to R cube. So what is the dimension of T? The dimension of T will be 3. What is the rank? Number of non-zero rows, the rank will be 3. And what is the nullity? So by the rank nullity theorem we will see that it will be equal to 0. Similarly, the second part, transformation of R square to R cube. R square means we have 2 columns. R cube means we have 3 rows. So in this way we can find that what is the dimension of T. So we can, what is the rank of T? Rank of T will be 2. In this way we can solve it. So matrix of a linear transformation. To represent a matrix, we can represent a matrix. A transformation is given, we can represent a matrix like 2x plus x2 minus x3. We can write the coefficient here. Then after that there is a second, we can write the coefficient here. Then lastly 3x2 plus 4x3. So we can write from here and just solve them we can, what are the benefits? Three reasons for matrix representation of a linear transformation. It is simple to write, it is simple to read, it is easy to more adapted. So it is the last question. It says that find the standard matrix of a linear transformation R cube to R cube where T x y will be equal to this. For example, this is our equation number 1, and we will say that a transformation of E1 will be E1 means standard, so we can write transformation of 1 0 0. So from equation number 1 we can write x minus 2y and 1 minus 2 into 0 plus comma 2 into x and 2 into 1 plus y, that is 0. So when we solve, we will get 1 2. Similarly, transformation of E2 we will got minus 2 1. Transformation of E3 we got 0 0. So in this way we will find the whole matrix. Just combine all these things, we will got the whole matrix. That is this. We can cross check it. So it is the end of today's lecture. If you have any question, then you can ask me. Okay. Okay, let's wait a minute. I'm going to take attendance.